continuing on with class 8, and we just did the crank slider. So now we're going to do the slider crank. And so here's the setup for the slider crank. We have the vector loop equation. We can write it out in the terms of the x right here. Here's x and here's y. Writing this thing out longhand. And we assume that theta 1 is going to be 0 and that theta 4 is going to be 90 right there, right? So those are things that we know, and we know the lengths of them. And here, this is a slider crank instead of a crank slider. The input is going to be d, right? So this distance is something that we know, and now we want to try to find what the two unknown angles are. They're going to be theta 2 and theta 3. So what we're going to do, so this is some things that we might want to know as part of this, some helpful mathematics. In order to be able to solve these into equations that are easy to manipulate, we want to use identities many of them are begin with this sine squared of theta plus cosine squared of theta equals to 1. Right, so you might know that from trigonometry. Some additional manipulations, as I've shown them down here, can lead us to these identities right here. Right, so like if we have these tangent squared of these half angle identities with tangent, allow us to break this thing apart. Right, and so we kind of need that stuff in order to be able to really walk our way and see where we get these equations from. Okay, so here's the slider crank, as I mentioned, and there's the vector loop equation there, marching through there, and that we can break it down into x and y if we assume that theta 1 is equal to 0, which is not a bad assumption, and that theta 4, which you can't really make out right here, but it really is talking about how the perpendicularity of the base to the horizontal is fine. That we can reduce those two equations into this. The constants, therefore, because of that assumption, are the lengths and theta 1 and theta 4. The input is going to be d, and now we need theta 2 and theta 3. So we're going to need to use some serious trig to be able to get pi some things, and one of the most useful things is that we have this cosine of an angle is equal to these half angle identities, and I have some proof down here. I say that it's in the last page of class 8 notes, and I hope it is. So here you go. I think I marched through the thing right here. Okay, so we rearrange and we isolate these equations right here. We're going to rearrange these and we're going to isolate theta 3. Come on. There you go. All right, so we have this. So those are the two equations that we had in the previous one. We're going to square both sides of these together, square both sides, and then add them together so that we can try. Our goal here is to try to solve for theta 3. Let me say that these are considered, I believe, transcendental equations. That's what makes them difficult to solve. I think I'm using the correct mathematical term. Transcendental equations, but you can see what we've done here. We squared this one, squared that one. What we're really trying to do is get, let me see if I go back to this right here. We're really trying to do this right here. We're trying to turn that into equal to 1, right? So you will see that's what we're doing there, is we're trying to put that right there. We're trying to make that into 1, right? So that's what we've done right there, and we've and then when we square these right there, of course we're going to use their little FOIL thing, and then these things are going to be drawn out, and we're going to collect some terms. When we collect some terms, we're going to see another spot right here. Well, no, wait a minute, that's not true. I was about to say that was going to turn into 1. Maybe. I don't know if that a squared might not belong in there. I'm taking a closer look at that. AC, AD. We see we have this C. Yeah, I think that a squared doesn't belong in there. Let me back out of this and fix that. These things happen right in here because I wrote these out myself right here. So I want to double check there. There's the a squared. Yeah, that needs to go out of there. So let me see if that is also included. Yep, it is. I need to fix that in my notes somewhere. Let's see if I fixed it in my other notes down in here. Well, I'm glad I'm doing that now instead of later. Yep, that a squared needed to go away. So I'm going to fix them later on. Okay, so back at it. Okay, so so that's like our motivation in this algebra is to try to get rid of some terms, right? So that's what we're trying to do. So we get rid of some terms, and so now we got theta 2 isolated mostly. So this is Norton's method from right here, trying to isolate some things out to try to stay organized. So he creates these k constants, and so he replaces like this whole thing right here with k1, and he replaces this with k2 and this with k3 right there, right? So we have one equation, and he's not the only person to do this, by the way. I need to look up the source. I think there's a guy named Freudenstein. That's the name that jumps out. I probably butchered that, but we're going to look that up and we're going to find that that's an actual thing. Let me pause and see if I can find it. Yeah, so here is at least one paper where they're talking about the Freudenstein equations and talking about its application to this. So let's come back to here. Anyway, we have this equation, and now we're going to try to solve it. In order to solve it, we use the half-angle identities right here, the tangent half-angle identities, and we replace the sine here with this, and the cosine here, right here with these. All right, and the usefulness of this is now that we don't have a sine and a cosine, we're dealing with all tangents, and as we pick the thing apart, we can reduce it down into a quadratic equation right there. That's our goal right here, as we've played around with this thing, and so now what we could do is we could just solve for the possible solutions of these the simplified equation right here, right? So and that's another thing that he does is he replaces those k's with a, b, and c. I know, it's crazy right there. So there's a, b, and c. We've replaced it in there. So now we have a quadratic equation with two roots, and we're able to find now solve for the theta 2, right? And there's two possible solutions right there with our plus and our minus. And then the theta 3's, they can be found just by going backwards into one of the original equations and thrown back in there. So it's quite the journey to be able to get here, right? So, but this really does lend itself to creating an Excel spreadsheet. So I will go through an example here. So we wanted to determine here for this problem for the slider crank all the possible values of theta 2 and theta 3, right, for a for the things that we know. And right here are the two solutions, by the way. I say first determine the top dead center, right here, location, and bottom dead center to ensure that we that the D is within its limits, right? So right here is the top dead center limit. Now here's the bottom dead center, right? That's as far as the thing is, as the piston can travel upwards, and far as the piston can travel downwards, right? And I think in class today I will be bringing my, I think I'll bring my slider crank here. All right, so let's go to it. Whoops, boom, make this a little higher. Okay, so and this is a long example, so I'm not sure if it's worth the time that's going to spend in class to do it. So here's the procedure by hand, not something that's a lot really pleasant. We're going to go through and find the K1 is a squared plus, oh, already getting it wrong, a squared minus b squared plus c squared plus d squared, right? So we put all those there. 40 squared minus 120 squared plus, right? So it's 40 squared, 120 squared, and then what did they say right here? Why 40, 20, 120, and 20 right there. Oh, and they said this was our input. Okay, so there it is. I couldn't find it there for a second. We have minus 20 squared plus our 100 squared. And we get a negative 2,400. Right, now we go K2. Right, so these are things, by the way, we should probably point out that were in the abbreviated version right here. Here's the abbreviated version, so we're plugging these things in there. We're really doing a plugging in, chugging job here by putting these things in there. And maybe I should fold this over here. As we're trying to put them in there. Okay, now we want to have the K2 is going to be a negative 2AC right there. So we take and we find negative 2A is 40 and C is going to be negative 20 right there, right? So we get 1,600. Then we get K3, negative 2AD. So negative 2 times our 40, and our D is going to be 100, we were told, right? That was their input. And we get a negative 8,000. Right? And now we need to get A, B, and C. So A is just going to be K1 minus K3, or our negative 2,400 minus our minus 8,000. So we end up with getting 5,600. And our B is going to be 2 times K2. It seems like a waste of time, but that's going to be our 1,600. I think I can do that in my head, 3,200. And then our C right here is just going to be K1 plus K2. So that's just going to be our negative 2,400 plus our 1,600. And so we get, did I do that? No. Did I do this wrong? One second. Okay, I wrote that wrong. K3. It should be K3. So that's a negative 8,000. So I get a negative 10,400. All right. Now we can find our theta 2. 1 and 2. So we get 2 times the inverse tangent of negative b plus or minus the square root of b squared minus 4ac over 2a. Right? And I didn't bother to plug in all of those values in there, so I'm not going to do it here either. We get a 95.80 degrees and a negative 118.4 degrees. Right? So if we use those, we can use those with theta 3 and theta 3 right here. Or we could just do this. You should check the distances and the angles to confirm. So we say a theta 3, 1 or 2 is going to be the cosine, inverse cosine of A over B times the cosine of theta 2 minus D over B, right there, right? And if I put that in there, I get 29.89 degrees right there. And let me double check something here. We should, when we check this, we're going to end up finding, okay, so we're going to use that, we can check this to find D right there, right? So one second here. Yeah, we want to check this angle right there, right? So we got this angle right here, 95.80 right there. And we want to check him with this 29.89, right? So I plugged him in there first, and then I got this out. So these two are associated with each other. I wanted to combine that with this equation right here. Plug them into both there and see what you get for D. So I solve for D, and that's going to be A times the cosine of theta 2 minus B times the cosine of theta 3. And what I end up finding is I get a negative 108.1 millimeters. And that's not possible. All right, so that's one of the things that I have to conclude by this. Something that I'm also going to get, let's see, I get a theta 3, 1, 2 right there. I didn't mean to put a comma right in there, but that's supposed to be subscript. And I'm going to try out my other angle right in there. So I'm going to try that out and put him back in. Okay, so let me see another second here. Yes, okay, so this one was with 2, 1. That's with this angle. Let me try this one again with instead this angle right in there. So I wrote the thing out as this way, but it's yeah, A over B cosine. Nope. Wait, I made a mistake here. I said cosine up here. I meant sine. I did do it with the right thing, but did I? I have to double check this right here. Okay, this is the D. This is the dB, so that should have been the cosine one right in there. All right, so the number that I just gave you, that 29.9, that's with the sine. That's with this one right here, the sine of theta 2, 1, and C over B. And then, so I got that, and I found out that that's not going to be possible when plugging them into there. And then I also tried the alternate angle 2, 2 right there, right? So that's this guy right here, and C over B, and plugging them in, and I got a negative 7.267 degrees right there. And then if I plug in for my D for the same one in that same equation right here, I get a 138.1 millimeters. It's also not possible, right? So these are not valid solutions to this. But now instead, what I can do is I can plug in for this equation right in there, right? That's why I'm saying you should plug in and check the angles to confirm. And if I do that now, on my theta 3, 1, I get the inverse sine of all of this stuff right here, and I think I wrote it out, a sine of theta 2 comma 1 minus c. All right, and these are both over b, so I guess I decided to do this over b for some reason. And then add pi to it, or add 180 degrees. What I end up is I get 150.1 degrees. And I check it, and that d ends up being 100 millimeters. So that is a valid answer. I do the same thing for here now. And I just want to double check that I did it for the cosine. Yeah. There's another version of this. So a theta 3, 2 here. And I do the inverse cosine of negative a cosine of theta 2, 2 minus c, or this right here. And I get b right there. And I add pi. And I don't see that I answered the question here. Did I run out of steam? I think I run out of steam here. That's not good. Adding these things back in there. Pause the video. Okay, so I identified what went wrong here. There's actually a mistake in the book. I'm pretty sure it's a mistake in the book. So the equation I should have used right here was the inverse sine right here in the positive. Okay, so let me show you where I'm getting this from in the book. And so I'm seeing that where I believe is to be a mistake right there. What they're saying that you should use when you get to right there into this spot to check the answers is to use these two equations right there, which are the solutions to the theta 3, right? So when we get to this spot right here and we find that we have these two solutions right here, we need to check them. And so right in here, I put in I put in the 95 point there for this one, and I get the 150. And then wait, let me see. Let me double check here. For some reason, we're doing pi plus the pi in there, but it works. It does work out. We do get the correct thing if we put this in here. If we do this, I end up getting 172.7 degrees. And if I plug that in, I will, if I check, I get 100 millimeters. So let me go ahead and put this back, show you the Excel for this right here, and I'll do that split screen thing here so we can double check on here. Yep, so here's our split screen. All right, so here's the process that we went through to be able to get to this. We put our inputs of 40, 120, and negative 120 into there, right? And here's our input of a 100. I get my K1, K2, and K3. So you can see these are the, I've used all of these, set this up. And then I get my A, B, and C. So I get all of those values right here. So now I get a solution. Here's my theta 2. So there's the quadratic equation right there. I'm taking the arctan of this, and here is my 95, right, 0.8, and my 118.4 right there. And then for my theta 3, 1, I'm going to try these out, right? So I try out this equation right here where I'm taking the arc sine of this and using this first theta. And I end up with an angle of 29.89 degrees, and then I do a check right in there. I just put it back in and see how big my the distance is going to be, and it comes out to that impossible to be, right? So that's where I got that right there. And then I try it again here, and I get this angle of negative 7.267 as part of the thing, and I put that back in there, and I get 138. Still can't be true. So now instead I try taking the alternate thing right here. Okay, so this one, wait, I gotta take this back. I actually used the cosine into this right here. So I went the cosine. I want to take a look at my book here. I took the did I take the cosine? Okay, I'm thinking about throwing away this whole video because I found like some mistakes that I was making in here. This was in fact a sine that was up right in there, okay, as I was coming through there. And as I'm doing this, adding this angle onto the thing, I think that this is not this isn't in fact necessary to do at times. I think what we can do instead is go back to the fundamental relationship that we're working with, and that is right here at the very beginning, right in there, right? So once we have theta 2, we can either use this equation right here or this equation to find theta 3 right here. So we either have a sines or we have a cosines. We don't mix the cosines and the sines up for this. So even in my spreadsheet, as I'm putting this there, and there's another video that I created that's showing how to make the spreadsheet. As I'm going through this right here and looking through, I think I've messed up, and in the later spreadsheet that I describe in the other video there, I have the thing actually working correctly, and it might just have some math error that was in here, right? So there's the sine ones that I've just shown that didn't work out. But these cosine ones, this cosine one does work out right there. You see that 150, and I get the check. I think this guy right here should actually, if I do this one correctly, so what I should have done maybe is just copied that back into there and copied that in here, and instead of that angle, used that angle. Boom, right there, yeah. So I actually get the right thing using the cosine ones. And so what I should have done as part of here, I think this, and this actually shows me using the sines right here. I use the sines plus the pi as part of that, and I use this, and you notice that I get the same answer right in there. So the important thing to go back to was what I was doing for the theta 3, right? I get the theta 2, and I get these two answers right here. And now I want to get the theta 3. I can go back and either use this equation right here or this equation to find that theta 3. But we have to be careful because sometimes we end up getting wrong answers by way of doing those. That's hopefully will be all I need to say as part of this video. and I'm going to end it because I have to go to some meeting.